And so first of all, let's start with a small intro. And so I have to tell you what is a homotopy sphere. And so a homotopy and sphere is just a manifold homotopy equivalent to the standard n sphere Sn is I will denote them by this x sigma. And actually we know that the Poincare conjecture holds in all dimensions in the topological case, so I could have as well said homeomorphic to Sn, right? Okay. What I will be interested in is what I will denote. I have no idea which letter this is. Theta.
It's a big theta,
Okay.
capital theta.
Yeah. And this is I want to say some set of homotopy spheres. It's actually a group, so I will need to justify that it's a group later. But let's say that this is the abelian group yes, okay. So the point is that since we know that the Poincare conjecture holds in the topological case, I could have as well said homeomorphic, but the Poincare conjecture doesn't hold in the smooth case. So we know that there are manifolds which are homeomorphic to Sn, but which have different, let's say, different smooth structures, so which are not diffeomorphic to Sn. And this is the phenomenon that we want to explore somehow. And so this set or this group is some group that will express this difference, let's say, or classify those manifolds, right? Okay, so this will be the abelian group of oriented H-cobordism classes of oriented homotopy n spheres. So this is a little bit of a technical description of this group. I need to explain probably what is an H-cobordism. So an H-cobordism is just, well, so let's say an H-cobordism between sigma 1 and sigma 2. Well, it's just a cobordism between those two manifolds. So an n plus 1 dimensional manifold. Wait, I should have put it downstairs. Indices. So an n plus 1 dimensional manifold which has those two manifolds as boundary. The disjoint union of those two manifolds. And an H cobordism is such a cobordism that the inclusion, so let's call the whole cobordism W, that both the inclusions of the boundaries are homotopy equivalences. So again, this is some group where we have oriented homotopy n spheres, and two n spheres are considered the same or belong to the same class if there exists such an H cobordism between them. This is a little bit of a technical definition, so maybe a better or more intuitive way to think about that group is as okay, I will first denote it slightly differently. This will be the abelian group of oriented diffeomorphism classes of oriented homotopy n spheres. And from what I said at the beginning about the smooth Poincare conjecture not being valid, and us wanting to distinguish, to look at this difference, this is actually what would interest us, right? And it is a consequence of some result called the S-cobordism theorem, that in dimensions greater than equal to 5, those two things are actually isomorphic. And actually, they are also isomorphic in lower dimensions except for dimension 4. So only for n equal to 4, those two things are distinct. Otherwise, they are the same.
I think it's open whether they are distinct. It's not known, I think. Or am I saying it wrong? Well, how do we write it?
Oh, okay, maybe, yeah.
So, yeah, I think it's. I can maybe.
Yeah, isn't there a counter example for the S-cobordism theorem?
So it's known that the H-cobordism theorem does not hold in dimension 4,
Yeah.
but for general manifolds, and I think it's not known if you ask that the pieces are spheres.
Ah, okay. I thought there is like a counter example with spheres, but I'm not sure.
I think. So I think that the counterexamples are not with spheres,
Okay.
and therefore it's I think open.
Okay.
And yeah, and by the way, so the map goes the other direction,
Yeah.
and maybe it would be so diffeomorphism implies H-cobordism,
Yes.
and
Yes, but not the other way around.
in any dimension, right? And the H-cobordism theorem tells you that in 4 greater than 5, you have this, and in so I think okay, well, carry on then at some point else. On dimension 4, yeah.
Okay, so this is the object
Yes,
that will interest us.
Does it mean oriented diffeom? It's like orientation preserving?
Orientation preserving, yeah.
Sorry. Yeah, orientation preserving diffeomorphism. Sorry. So this is the object that will interest us, and what I will show you via applying smooth surgery theory is how to reduce this problem. So via smooth I will reduce this problem that is obviously geometric to some problem is stable homotopy theory. So what surgery theory cannot do directly is like calculate to what is this group isomorphic to. We will reduce it to a problem is stable homotopy theory, which is then the result. The solution of this problem is already. Okay, so and more specifically, what is the problem in stable homotopy theory? It's the let's say calculation of the so-called J homomorphism, which is a homomorphism going from well, actually, I should say it's a collection of homomorphisms for each n. Which go from the homotopy groups of the group SO to.
It's really a difference of 1 dimensions, or
Sorry?
is it really the 2 dimensions?
Yeah, it could have been pi n of BSO,
okay.
or pi n minus 1.
Okay.
but I think I think it's more usually this is what is called the J.
No, it's pi n of SO into pi n stable, isn't it? Or yeah, it's from pi n SO into pi n stable.
Wait. Yeah, right, because okay, sorry, yeah. Here yeah. I forgot that here it's also BG, then it's G.
Okay.
Yeah, sorry. So this is the J homomorphism, and we will see that. So our question of classification of this can be reduced to just some statements about the J homomorphism. Okay, so let's do it. Maybe a quick summary of what I will go through. So the plan is the following. First, I will give some kind, I would like to call it a crash course into surgery theory, but it will be even faster. So I will show the strategy of surgery theory. I will try to describe it very, very quickly. Then I will show you, I will present the main result of surgery theory and main tool also, which is the surgery exact sequence. And I will explain the terms in this sequence and also the maps. Then I will look at how does this surgery exact sequence look like, what does it look like for spheres. So surgery exact sequence for Sn. This case will be for a general smooth manifold, closed smooth manifold. And then I will try to solve this question for Sn, and first in the odd dimensional case and then in the even dimensional case. And then possibly there will be some more things I will say if there is time, but we will see how it goes. I expect today to be able to get probably this far if everything goes well. We'll see. Okay, so let's start. So let's talk about the strategy of surgery theory. Let me pose this kind of problem, which is given a smooth manifold X, n-dimensional smooth manifold. I want to know, I would like to classify the manifolds that are homotopy equivalent to it up to diffeomorphism, but let me state it in a slightly different way. So given this manifold, classify all homotopy equivalencies up to diffeomorphism. And
So you demand that M is also a closed.
well, yes, I demand that M is a closed smooth manifold. And what I mean by classifying homotopy equivalencies up to a diffeomorphism means that two such manifolds are in the same class if there exists a diffeomorphism between them. Maybe I'll call it G. is a homotopy equivalence, this is a homotopy equivalence, such that this square commutes up to homotopy. What we mean is that F1 is homotopy to G composed with F2. It is
the other way around.
these two?
Yeah,
Or,
yeah.
okay, yeah.
Well, first G and then F2, right?
Yeah, I tend to denote the composition in this way.
Ah, that's it.
Okay. Yeah. So this is slightly different than just looking at diffeomorphism classes of manifolds that are homotopy equivalent to X, because in this case we can have one manifold, and one can belong actually to two different classes, because we can have two different homotopy equivalences from the manifold to X. Okay. So this is the problem that we want to solve, and the rough strategy how we will address it is that we will start with a map. We will start with a smooth closed manifold M, and just sum a map into X. Let's just stay with the fact that this is some map, and we will perform a so-called surgery step. And this surgery step is some geometric procedure. So I will denote often things like that as just pairs M and F. And the surgery step is a geometric procedure how to get from one such pair to another pair M prime F prime in a controlled way. And by in a controlled way, I mean that we can track what happens on homology after doing that. So, which means that here, since we have a map from M to X, this map, of course, induces maps on homology, and by performing the surgery step, we can track how this induced map on homology changes after the surgery step. So we get some new map and we know what this map is. And now, what we are trying to achieve is, after finitely many such surgery steps, to arrive at a map which gives us isomorphisms on homology. So, to some F star, okay. Then we arrive to a map which gives us isomorphisms on homology. And why is that interesting? Why is that important? I will not go into that, but well, we know from homotopy theory that using the Whitehead theorem and the Hurewicz theorem, we can prove that this would actually imply that F is then a homotopy equivalence. So for such a map to be a homotopy equivalence, it is enough that it induces isomorphisms on homology.
If you say it like this, then maybe you should just restrict to the simply connected case. So if you, I mean, which we are now.
Yeah, okay, so
in
the non-simply connected case, we will use local coefficients.
It's more complicated, let's
Yeah.
say. Let's say that we don't want to-
Okay. And so So what is actually the geometric procedure of the surgery step? Well, it is similar to cell attachment. So we know that for CW complexes we can attach cells to a CW complex in order to kill some elements. Well, in order to, let's say, change the induced map on homotopy groups. So what we want to do the same thing for manifolds, but the problem is that by attaching the cell to a smooth manifold, we don't get a smooth manifold anymore. So what we need to do instead is we will attach some kind of a, it's not a thickened cell, but it's like, let's say, a tubular cell. So instead of a cell dm plus 1, we attach something like this. Sorry, dk plus 1. We attach some the product of this cell with Sn minus K minus 1, so which is some kind of a, we can imagine as some kind of tubular cell, right? Where n is of course the dimension of the manifold we are doing surgery on, and k is a number from 0 to 2. Okay. So we attach this. But of course, in order to attach this, we must first cut out of the manifold a copy of an embedded sk minus times dn minus k, right? And then those two things have the same boundary, and we do them along this boundary. This is the surgery step, and I want to maybe show it on some very simple example. How does it work, and so that it maybe hopefully gets clearer. So the example I will take is I will start with such a map where M is the torus, 32 of course. And the map is into the two-dimensional sphere, and the map is question will actually be the collapse map. So I start with the torus. I have a map into the sphere, and where should I leave this? Good. And so actually I wanted to draw the sphere like this. We have an embedded disk here, and the collapse map takes this disk to the whole sphere minus the north pole and the complement, the interior of this disk, and the complement of the interior of this disk is taken to the north pole. This is the collapse map. Okay, and so now let's look at the homology of those two manifolds. So here the first homology group is isomorphic to direct sum of z's. Second homology group is z. Here the first homology group is of course 0, and second one is z. So, and obviously the induced map on homology in this case is the 0 map, in this case it's an isomorphism. Okay, so what we want to do is we want to take an element from the kernel of the map induced on the first homology, which is, for example, this S1 here, and we want to perform surgery in it. So we perform the surgery step on this S1, which means that in this case we cut out S1 times D1, and then we attach to it D2 times S0. So let's do it. What happens is that we have our torus. We take this S1 times D1, we cut it out, and we glue just 2 copies of the 2-dimensional disk. So what do we get? Something like this. Right, so okay, very bad drawing, but so we get something like this. Now the point is that at the end of this procedure, what we get is not only a new manifold, but also a map to the sphere. Yeah. And this map can now be seen to be a homotopy class. And the strategy of surgery is doing this procedure also for higher dimensional manifolds and therefore for higher homotopy groups. And the question is whether starting with such a pair, we can by a finite sequence of surgery steps convert it into such a homotopy equivalence, or we cannot. So now I will move to the surgery exact sequence.
So how much control do you have actually for this procedure? Because you picked an element in kernel and you eliminated that one, but you also eliminated anything which intersects with it. Because you have also the others.
Yeah, it's an important feature.
So you mean intersects like this other element, right? Okay, so in this special case, actually there's a big difference between doing surgery on odd-dimensional and even-dimensional manifolds. When they are even-dimensional,
You need to think of intersections for?
yes. Well, yeah, and the problem is that
Okay.
Well, you have actually, I think you should distinguish two things. First of all, if you have something n-dimensional, you do surgery up to the middle dimension. That is okay.
Yeah.
And then in the middle dimension, but in the middle dimension you have the same problem. And maybe you wanted to say something, maybe so.
Well, yeah. In the middle dimension, actually, yes, there is. This is the place where some obstruction arises, and the obstruction is given in terms of these intersections and also in terms of self-intersections, because I didn't talk about it. To do this surgery step, we need to find an embedded thing like this that represents the element of homology, which is not always possible. So that would be another kind of obstruction that arises there. And then for odd-dimensional manifolds, this doesn't happen, but the other problem is that so in odd-dimensional case we have some kind of 2 middle dimensions of homology, or 2 middle degrees. And by killing an element in one, we create an element in the other, and vice versa, or let's say.
Or even potentially in the same.
Yeah.
Yeah. It can be very complicated.
And this is another way that an obstruction arises in that case.
But this is a good case, and it's true that in it's a little paradoxical that when the first time sees it that you do surgery on, well, sort of one cement, but simultaneously you kill the other cement as well. So it's it can be explained very nicely, but I think you should just carry on.
Okay, so now we will look at the surgery exact sequence. Okay, let me write it out. So, okay, so this is the surgery exact sequence. Especially I will just talk about the smooth surgery exact sequence, which means that we are in the differentiable category, and I think I will just talk about the simple surgery exact sequence.
Well, it doesn't matter. I mean,
It
because
does.
we are in the simple connected situation. Okay,
Yeah, but so far I
so-
want to
so-
talk in general.
Okay,
here.
okay, fair enough.
Yes. So in general now we have a smooth closed manifold X, and for such a manifold we have this kind of exact sequence. And I will go through the terms, the maps, and so that it's maybe becomes a little bit clearer. So first thing I want to look at is this term. It's and this is the so-called smooth and simple structure set of the manifold X. And what is it? Well, it's actually the set that gives us the answer to this problem. So it is exactly the set of equivalence classes of homotopy equivalences from a closed smooth manifold to X. So this is a homotopy equivalence. And the equivalence relation,
Oh, it's the same.
it's the same as here. Okay, so this is the set that we are interested in among all those sets in the surgery exact sequence. Can you see this? Next, this set. Is the so-called normal invariance of X. And okay, so first of all, intuitively, this is we can think about this as like a pool or a collection of those kinds of pairs of manifold map on which we want to do this surgery. And we want to think of this collection or pool as divided into what I will call surgery orbits. So all pairs which I can link via surgery steps. So if I can come via finite amount of surgery steps from one pair to another, then they will belong to the same class. So intuitively, those are some kinds of surgery orbits of pairs like this. Okay, now let's look at how we could actually describe such a set. So what they really are is normal cobordism classes of degree 1 normal maps. To X. So first of all, let's explain what that means. First of all, what is a degree 1 normal map to X? Well, it is a manifold, smooth closed manifold, together with a map F, such that we have some vector bundle over X, and the map F is covered by a bundle map from the normal bundle over M, possibly stabilized, to our vector bundle over X. This means that it's a normal map, and that it's a map of degree 1 just means that F has to be a map of degree 1, where we have a notion of degree for maps not only from spheres to spheres, but also from closed manifolds. And it means the same thing on the nth homology is multiplication.
So we usually come up with these normal maps and normals invariants, like when we consider X to be Poincare complex.
Well, any manifold is a Poincare complex.
Yeah. So, but it's just that Poincare complex does not, I mean, in some sense it does not fully a manifold yet, but this normal map somehow emulated a normal bundle and stuff like that.
No. You mean only the setting where X is a Poincare complex, but M is a manifold. M is always a manifold.
Yeah, sure.
So you have a normal bundle you're considering only for M.
Yes. Normal bundle for M.
Yeah.
But for X, if it's Poincare complex, then
Well, there's just some bundle
Then-
psi. I
Yeah,
mean, you
yeah,
can
yeah.
consider bundles over any space. Doesn't matter whether it's.
well, I mean, if X is a manifold already, yes?
Yeah.
The psi is the normal bundle?
No.
Any bundle.
No. Even if X is a manifold, then psi is not necessarily the normal bundle of X. It's just some bundle such that it fits into such a diagram. So, and that's important that it varies, and that you need to consider the set where these psi's can be different than the normal. Okay, I think you will be.
For exotic spheres, you are taking exotic bundles.
We'll see. I think he is going to come to it. So maybe let's just.
Yeah. So there will be yet another description of this set that I will mention,
Mhm.
which maybe. Okay, but so far this is what the degree 1 normal map to X consists of. And so why do we require the map to be normal and of degree 1? Well, to say it simply, those are necessary conditions for the map F to be a homotopy equivalence. And those two properties are invariant under surgery. So if I do surgery on the degree 1 normal map, I get again a degree 1 normal map. This means that those are the maps that only interest me. So I can refine the statement. I do not choose just any pairs MF. I choose pairs where the F is a degree 1 normal map. Okay. There is another more technical reason, is that I need this bundle data to do the surgery step.
Yeah, but that's
I will
too
not go
technical
into
for
that.
this.
I will not go into that. I will just mention that the degree 1 normal map can be given also equivalently, not in terms of the normal bundle, but in terms of the tangent bundle of M. So actually, I can switch between those two, because that will. Good. And now what is a normal cobordism? So a normal cobordism between two degree 1 normal maps is, of course, cobordism between manifolds M1 and 2 with a map to X times 0, 1, X times interval. And to simplify it a little bit, I will just say that such a map that on the boundary, this is the degree 1 normal at F1, this is the degree 1 normal at F2, and everything is covered by bundle data. Appropriately.
And now W is really a cobordism. It's not, does not have to be an H cobordism. So yeah, I mean, I like to write a hole in it.
Okay. Good idea.
Indicate that.
So any colors.
Okay. And yeah, and maybe, I mean, for Marian, I mean, he will be talking about cobordisms at the end. But one thing that's important maybe for him to know is that if you have manifolds, so if you start with a manifold, you perform surgery, you obtain a manifold that's cobordant.
Yeah, I
And-
wanted to.
And
yeah.
okay,
Yeah,
I thought you were going to. Okay, so you just say what?
Yeah, so as you said, so if I have a manifold, I do surgery on it, the resulting manifold is cobordant to the initial one. And actually, so I explained how this relates to the intuitive picture. This relates to it also because any such normal cobordism, so let's say I have M, I don't know, 2 or whatever, M1, any such normal cobordism can be, I would say, somehow cut up into some simple cobordisms, simple normal cobordisms, where this is like M1 prime, M1, blah blah blah, where a simple cobordism is obtained just by one surgery step.
Yeah, so I think the good terminology here is it's called elementary, just because
Yeah.
the word simple is used for other.
Okay.
Okay, so it's called elementary cobordism. That's the one that's obtained by surgery, and any cobordism can be decomposed into such. Yeah.
Where we
So
get
that-
from one boundary element to the other by one surgery step. And this is the reason why we consider normal cobordisms, because they exactly correspond to these surgery orbits.
Yep.
So any two elements in the same class, we can connect them by a finite amount of surgery steps. Okay, so we have this set of normal invariants, and
this whole setup is moving forward because we have the collection of homotopy equivalences, right?
Sorry?
We have collection of FIs from MI to X, and then we are doing all this thing, right?
What is all this thing?
What's the question?
So we have the collection of FIs from MIs to X, right? And then we are looking at the diffeomorphisms.
The normal maps of degree 1, right?
Yeah, whatever. This in structure set or in normal invariant, wherever. So we have those collections.
So you want to ask whether I'm...
So we are,
I'm not dealing with the existence question of like where X is a Poincare complex and we wonder whether there is some manifold structure or not. No, this I'm skipping over. I'm directly going to the surgery of that sequence. I'm assuming it exists.
Yeah.
Okay.
otherwise we will have this Pontryagin-Thom construction, all those things, right?
Well, this we would have also here. I didn't want to go into it because it's complicated. Or should I
No.
describe it? No, I don't think so.
That's
But yeah.
Is there a space with empty normal invariants?
Well, empty. I mean, there is always one element. Which is empty.
No, with
No,
What do you mean?
If X
A Poincare complex or what?
if X is manifold, then I think identity is
Yeah.
Always
is
there.
there, but
Yeah.
if X is Poincare, then
Yeah.
maybe.
Then there are for example, in Simona's thesis, master thesis, she had a very concrete example of a.
So there is an alternate way to describe this set is that it's the set of reductions of a Spivak.
Yeah. So, but
If
I
it
think we
doesn't
don't
have-
want to fall
yeah.
into this. So the answer is yes, but I think it's a for a different topic.
Okay. And so and now the question becomes choosing some class in here. Does it contain a homotopy equivalence, let's say, instead? So does it contain, choosing one surgery orbit, is there in this surgery orbit a manifold with a homotopy equivalence to X or not? And as it happens, there is actually only one obstruction to their existing such a homotopy equivalence. So okay. And this obstruction will be called the surgery obstruction, obviously. And it lives in this group, the nth L group of the group ring of where the group is the fundamental group of my manifold X. And this is the surgery obstruction map. So I will just briefly talk about it. So obviously the surgery obstruction maps some surgery orbit or some normal cobordism class to its surgery obstruction. If it's 0, then there is a homotopy equivalence in that class. If it's non-zero, then there is no homotopy equivalence in this class. And
I think for that stuff to hold, we required it to be simply connected.
for which stuff to hold?
I think that the homology equivalence, homology isomorphism implies homotopy equivalence.
Yes, that's what.
Yeah, I mean, I was
It
saying
work
you
out
can
also.
modify it for the non-simply connected case, but it's more complicated, and I think these two talks we don't want to go into it because the you are in the simply connected
Yeah.
situation, so we want to.
So I'll be talking about
So by
homotopy
one
stage.
step, so then
Because this is the, I'm just
Well,
showing the
I mean, you have
surgery
to
exact sequence for the
use
general
you have to use homology
with all
of the universal cover considered as a set by one module. That's basically what you have to do, and that's more complicated. But okay.
And then it works out in the non-simply connected cases.
In our case, last term is just z or z for 0.
Yeah, okay.
So this is the nth L group of the ring Z by 1x, and basically what it is a group of some stable isomorphism classes of quadratic forms over this grouping. And I don't want to talk anymore about it now. I think Saki will talk about this in his
Yeah,
talk
so
a little bit. And so okay, so that's that. And I have yet to tell you. So now I want to talk about this map beta. Zeta.
In simply connected case, we actually know these L groups, right?
Yeah, that's what I will.
You can just write
in a while.
down.
Yeah. So what is this map? Well, it's not hard to figure out. It takes some class of homotopy equivalences to X to some class of degree 1 normal maps in X. So in other words, it takes a homotopy equivalence like this to this degree 1 normal map. Now I'm using the tangent bundle interpretation of the normal maps. So since this is a homotopy equivalence, we have a map F inverse from X to M, and we can pull back the tangent bundle by this map, and then this map obviously covers our map.
And so in particular, this is related to what Sari was telling you before. So that's an important thing, that if you have a homotopy equivalence of manifolds and you pull back the tangent bundle of the target, you don't necessarily get the tangent bundle of the source. That's so homotopy equivalences don't preserve tangent bundles.
Yeah. Yeah, so actually even just elements of the image of this map can be elements with where you don't have the tangent bundle, but some other.
Yeah.
Pull back or push forward?
Sorry?
It's pullback.
It's pullback of the
Like
inverse.
F inverse. So F inverse goes in
Okay.
the direction and then it's pullback. Yeah. So this is the map, and I will not show now that it's well defined. It's not hard to check it and so on. But what is important is that from what I said here, that actually the surgery obstruction is indeed the only obstruction to finding a homotopy equivalence in some surgery orbit. It follows that in here this sequence actually is exact. So the kernel sigma is equal to the theta. Now,
Well, maybe just be a little bit careful. Using by kernel, the point is that the normal elements can be made always into a group, but the map sigma is not always home. So you mean pre-image of 0.
yeah, pretty much.
It's, okay.
So yes,
It's, you,
I wanted to mention the dinner, but the
Yeah.
surgery exact sequence is not an exact sequence of groups, it is an exact sequence of pointed sets.
Yeah.
So each of those is a pointed set,
Yeah.
and by kernel we mean the preimage of the point we chose. Okay. So now we see that we have further elements on the left side, but actually those have the same interpretation as the terms I have just explained, just for some manifold with boundaries, especially in this case for x times interval, and they have an interpretation relative boundary, which I mean that in all those constructions we assume that we have diffeomorphisms on the boundary. So it's like we discard the boundary and do stuff on the inside. And the last thing I want to say
How does this sequence continues to the left?
to the left.
Yes.
So you don't take times interval, but times d2 relative boundary of d2 and so on. Two-dimensional disk, three-dimensional disk, and so on. Okay, and the last thing I want to mention is this map. And this map comes from is a consequence of the fact that we actually have an action of this group on the set, on the structure set. So there exists an action I will not write x times interval, I will just write x. It's obvious that the fundamental groups are the same, right? Of those two manifolds. So there is a group action of this group of this set. It is the consequence of the so-called Wall's realization theorem. And the point is, the construction is, the point is that given some element, let's call it omega bar, in this group, and given an element in this set, so some homotopy equivalence to x, we can find, what can we find? We can find some cobordism W such that F is now a map of normal map of degree 1 to x times 0, 1, where here we have our M1, here we have the homotopy equivalence F1, and on the top boundary we have some closed smooth manifold M2 with a map F2, where F2 is also a homotopy equivalence. So in other words, if you give me a manifold Fm1 with a homotopy equivalence to X, and Okay, sorry. What I should say is that where does this element come into this game? This is the element. This is the surgery of. This is the surgery obstruction of this cobordism W. So this is the surgery obstruction to transforming the map F to a homotopy equivalence relative boundary.
Okay. It's really cobordism again. I would maybe write a hole in it.
Yeah.
Draw a hole.
Where this omega bar is the surgery obstruction to transforming F into a homotopy equivalence relative boundary. And in this way, this group acts on this set. Especially in what way we choose this M1, F1 to be the identity, X and identity. So we fix one element in here, it's the identity element, and then since this is an action, different elements in here give me different elements in there, and this is the map.
Well, you don't know. I mean, possibly
Possibly
different
elements.
elements.
Yeah, possibly.
So,
Yeah.
so this is a method, by the way, of constructing possibly non-trivial elements in X. So if you have this theorem, then yeah. It may give you.
Okay, so let's go.
So maybe while you will be erasing, I want to maybe get back to the question that you had about the surgery killing both classes. I mean, if you look there, you are attaching disk times a sphere and you cut out sphere times a disk. So cutting that disk kills one class and adding the other kills the other class. So that's the another way of seeing that both classes are. But okay, let's.
To the special case of the surgery exact sequence for the sphere. Okay. Let me just write part of it. I forgot the other interpretation of normal units, right?
I don't know what you want to say, so.
Okay, answer. So before I get to that, I forgot that I wanted to give yet another description of this normal units. So we do it here. So in general, for this set of normal invariants, there actually exists a classifying space. So which is called G model. And so, what does it mean? So, it's such a space that the normal invariance can be described as the set of homotopy of classes of maps from X to G model. And I just want to maybe talk a little bit about what is this space, how does it come to be, and so on. So, first of all, we know that we have the classifying space BSO, which is the classifying space for vector bundles. We have also a space called BG, which is the classifying space for spherical fibration. So stable spherical
I think
fibration.
you should either have BO and BG or BSO and BSG. But
Yeah, okay, you're right, yes. Or maybe let's say B and
yeah.
So this is the classifying space for spherical fibrations over spaces, topological spaces. And where should I go into it? What corresponds to vector bundle isomorphism here is some notion of strong fiber homotopy equivalence.
Yeah.
But we can maybe view it as like on vector bundles you need to have isomorphisms on fibers as vector spaces. Here you need to have homotopy equivalences of fibers. So, and there is actually a map from this space to this space. And I will call it very suggestively J, let's say twiddle or whatever. And how is this map given? Well, over the space, we know that over the space BO we have some kind of, okay, no, so over,
Does G stands for something?
which one? This one? This G?
Yeah, for
Yeah, it's, okay, so yes, so the same way that as O stands for the orthogonal group, G stands for the group of well, let's say self-homeomorphisms,
No, homotopy.
self-homotopy.
And it's actually not a group, it's a group-like monoid. It's a topological monoid whose I0 is a group.
G, and I should say this is Gn of, oh, it's a monoid, yes, sorry, of course. So it's a monoid of self-homotopy equivalences of Sn, and G is just the colimit of those spaces. And so what's this map J twiddle? We know that over the classifying space BON we have a universal bundle. And gamma n is usually how it's called. So this is a vector bundle over this space, and if we consider its sphere bundle, so if we restrict to its sphere bundle, well, this is obviously a spherical fibration over that space. So it must have a classifying map into BG. So there must exist a map, J riddle I call it, of, and yeah, BO into BG, which corresponds to this bundle via
Pullback.
the pullback of some universal vibration. This is the map J twiddle. Now, we have some map of topological spaces, and there is a construction. It's called the construction of a path space vibration, which allows us to transform any map into a vibration. So it allows us to transform a map from topological space to topological space to a map from a homotopy equivalent topological space, but which is a vibration. So we have a term in here making it into a fibration. And if we do that, well, the fiber of this map is called the homotopy fiber of this J0. And this is the space G model. Okay, this is the space G model. And how can we describe it? Well, no, let me say first this. Having a fibration like this, I can take homotopy classes of maps from any space into those spaces, and what I get is a long exact sequence of groups. So what I get is G model and here I would have comes from X to the loop space of B. Here I would get the loop space of BO. And so on. And what is important now, so we know that we are interested in this. These are the normal invariants. So here we have spherical fibrations over X up to strong fiber homotopy equivalence.
Isn't the loop space of B G is G?
Yeah.
Yes. So this would be.
Yeah, I mean, but it's not important.
Spherical fibrations over X up to strong fiber homotopy equivalence. This is okay. I should have said also stable strong. But okay, this is stable isomorphism classes of vector bundles over X. And from the construction of the path space fibration, we can figure out that what this will be isomorphism classes of pairs like this of a vector bundle over X and T, where T is a fiber homotopic trivialization of the vector bundle. Of the sphere bundle of the sphere bundle of psi. In other words, in here we have I should have okay, there is some isomorphism relation between them, doesn't matter. In other words, here we have vector bundles yes, so one vector bundle could possibly belong to different classes if we choose different trivializations. Okay. And so in here, Sergey, you can see what you asked, that actually, so the bundles in here for
They
the
can-
definition of the normal maps.
Yeah, they can vary, but they cannot be really totally arbitrary.
Yes.
I mean, somehow by this, you know that all of them, they have to be equivalent as spherical fibrations. But they may definitely be different as vector bundles.
And why is it important that I mentioned this other definition of the normal invariance? Is that because it's exactly by switching. So if you look at it, this is somewhat of a geometrical definition. This is a homotopy theoretical definition, so the definition by stable homotopy, and it's exactly via switching between these two views that we will accomplish what we wanted, so to reduce the problem of finding the group of homotopy spheres, some geometrical problems, to problems in stable homotopy theory. And the switching between these two views happens mainly via Pointryagin construction, but I will not mention the Pointryagin construction here.
But the key idea why this comes into the game is that if you have the homotopy cons, you can do that pullback construction that you did there, and so the point is that F inverse upper star TEM, or actually it's better to do it with the normal bundles, but that doesn't really matter that much. Well, the point is that you may get these different bundles over X, but they will all be as spherical fibrations will be fiber homotopy cons. So this is exactly the freedom that you want to allow there. You want to have different bundles, but they all have to be as spherical fibrations equivalent.
Yeah.
Okay.
You mentioned there that we actually have that map not for BO but the spherical bundle of that gamma n. Yes.
Sorry? Which one?
The J twiddle,
Yeah.
yeah, or that map or that one. So you've had the universal bundle over BON, yes. But you then said that we take the sphere bundle of that universal bundle.
Yes.
And that has a
This is
classifying.
the map classifying it. So
So
Sphere bundles-
that map classifies like it goes not from B or how it is.
no, so
Gamma
If we
n
have-
is a pullback of some bundle over BG.
Yeah.
No. The associated spherical fibration is a pullback of the spherical fibration.
So since BG is the classifying space for spherical fibrations, we have a bijection like this, right? So any spherical bijection over BO corresponds to some map from BO to BG. And this is what happens here. This is a spherical fibration over BO, and okay, and yeah, I didn't mention the
Yeah,
n.
but
So
okay.
of course I have some GNs, and then by taking the colimit, I get some.
Yeah.
Right.
Yeah.
But the point is that the map is actually from BO to BG, and how it classifies is you get this bundle by the pullback of some universal bundle over this via this map. Okay, and now let's look into the surgery exact sequence for the sphere. I hope that I can finish this at least. Time. Okay. So first of all, and I will write this into some lemmas. So that I have some lemmas on the board. First of all, what I claim is that the structure set is actually in bijection with the group of homotopy spheres as I defined it here.
This is
And
for n bigger or equal than 5. Okay.
yes, all that I will be doing. So I forgot to mention it that the surgery exact sequence exists for manifolds of dimension bigger than or equal to 5. Is exact for dimension, and so everywhere I will assume that that is bigger than or equal to 5.
But
And-
yeah.
So let's see how this goes. This is the set of equivalence classes